Today we shall learn about the concepts of power factor. The objective of this lecture is to learn to calculate the power factor for any load for a given source voltage wave shape. That is what you will be able to do at the end of this lecture. Based on the above objective, this is the lecture flow. First, we shall see what a power factor is, what is it all about. Next, we should see how to go about measuring the power factor or calculating the power factor from the measured power, and then we shall see few examples. So, the first topic, which is what is power factor. First, consider the following circuit. It is a simple circuit with a voltage source of an arbitrary wave shape and also consists of a resistance. It is a resistive load, and as shown in the diagram, there is a current I also flowing through it. Now, let me ask a question. For a sinusoidal voltage wave shape, how will the source voltage wave shape and correspondingly the current wave shape look like under steady state conditions, that is. So, let us look at that. So, we have here the x axis, which is the time axis, the y axis the amplitudes, the black curve is the voltage wave shape, which is the sinusoidal voltage wave shape, which is the source voltage. The red curve, as you see, is the current wave shape. So, for a resistive load, pretty simple, you see that the current is in phase with the voltage, because it is just V by R. Now, consider instead of a resistive circuit, an inductive circuit. The load is inductive, okay. The R is being replaced by L here, as you see. Now, what happens if we apply a sinusoidal voltage to this inductor under steady state conditions? You see the same time axis, that is the x axis is time t and the y axis is the voltage. Voltage being black in color as usual and the current is red in color. What do you see? What is the difference between the previous voltage wave shape in the case of the resistive load and that of now with the inductive load? You see that the current lags the voltage. The current crosses the 0 and goes positive much later than the voltage wave shape, which started going positive, crossing 0 right at the origin. So, basically we see that in the case of the inductive circuit, the current is lagging the voltage. Now, let us consider one more modification, that is a capacitive circuit. Here the load is a capacitive. Let us apply the same sinusoidal voltage wave shape to this capacitor or this capacitive load and see what happens to the current wave shape under steady state conditions again. So, we see again here the same familiar axis, the time axis t, the amplitude axis with the source voltage being black in color, the current being red in color. See the difference here. Here the current is crossing the 0 going positive before the voltage source goes positive towards the end of the circuit, or in other words, if you look towards the origin of the origin, when the voltage is crossing 0 and going positive, the current is already positive, which means the current is leading the voltage. So, in all capacitive circuits, as you know, the current will lead the voltage waveform. Therefore, they are called the lead networks, and the inductors, as the current lag the voltage, they are called the lag networks. Let us compare all the three circuits here. You have the resistive circuit, the R network, the L load, that is the inductive load, the C load, the capacitive load, all three put side by side there, and the corresponding voltage source waveforms, which are all sinusoidal in all the three cases, and the corresponding currents. Currents are all in red in color as usual, and you see that the current for the resistive load is in phase with the voltage, the current for the inductive is lagging the voltage, and the current for the capacitive is leading the voltage. Why have I taken only these three types of loads? Generally, if you see, when energy is flowing from source to the destination, what all can happen to the energy? There are only four things that can happen. One, the energy while flowing from the source to the destination can get dissipated, meaning it can become unavailable to the destination. Second, the energy can get stored. It can get stored in two ways. One is, it can get stored in the kinetic form as an inductor, where the energy is stored as half L I square. I is the flowing, and therefore, it is related to the kinetic form of energy storage. The other form of storage is the potential storage, like in a capacitor, where the energy storage is the form of half CV square. The effort or the voltage is the medium through which the energy gets stored. And there is also a fourth action that can happen, that is, energy can also get transformed from one domain to other. It can get transformed from electrical to magnetic, magnetic to electrical, electrical to mechanical, mechanical to hydraulic. All these transformations can occur as the energy flows from source to the destination. But if you see, the energy basically can get lost, that is, become unavailable, that is resistive load, or can get stored either as an inductive form, kinetic form, or a capacitive form, potential form. Okay. That is why these three basic types of loads, that is a pure resistance, a pure inductance, and a pure capacitance, are the ones that that equivalently exist in any complex networks. And therefore, these three are the ones that are basic to the understanding of the power factor also. Now, coming back here, consider the resistive load circuit. Now, in the resistive load circuit, we saw that the voltage source waveform and the resulting current waveform were like this. That is, you have the, as usual, the black voltage source waveform sinusoidal, and the current waveform which is red in color. Now, to this we shall apply a process, that is, we shall do a process. And what is the process? We will multiply the voltage waveform and the current waveform. What do we get? The voltage is in volts, the current is in amps. When you multiply V and I, we get watts. So, we will produce the power waveform in watts, the instantaneous power waveform. So, we are going to produce the waveform P, which is equal to V I, by multiplying these two signals every point by point, instant by instant. Okay. So, on multiplication, you see that there is one more waveform added on to the axis, the blue colored waveform, which is the instant by instant multiplication of the voltage and the current waveforms. Notice that at the origin, when the current and the voltage both are 0, power is 0, and gradually the power is positive, rising up, because both the currents and the voltages are positive. and then again at the 180 degree point voltage and current have become 0, power has become 0, and then further on both voltage and current becomes negative. So, product of that is still positive, and therefore, the power waveform continues to again rise up and become positive. So, you see some kind of a sinusoidal, it is a sinusoidal waveform, the blue colored waveform, the power waveform. It is shifted up, it does not have any negative component in this case, it has an offset and it has a frequency which is double the original voltage and current waveforms. Of course, we will come to the mathematics of that one later on, much later, but you try to understand the basic concepts graphically first. So, this is the power wave shape. Now, what is the average value? So, the average value, let us unclutter the graph, we remove the source voltage and the current waveforms, just keep the power waveform and the average. So, we have a finite average as indicated by the thick line shown on the graph. Incidentally, if we have Vm as the maximum source voltage and Im as the maximum current, then Vm Im by 2 will be the average. Okay. Next, consider the inductive load. In the case of the inductive load, we saw before actually this specific graph, the current lags the voltage as you see. Now, to this also we apply the same process, the process of multiplication, multiplying the voltage waveform and the current waveform to produce the power waveform. P is equal to Vi, and that we will sketch it in blue color. You see what happens, much different from the resistance waveform, isn't it? Here you see at towards the origin, that is at angle 0, the voltage is 0 trying to go positive, already the current is negative because it is a lagging circuit. At that point the power is 0 and the power starts going negative because voltage is positive, current is negative, and therefore, the product has to be negative. So, you have the sinusoidal, first the negative half coming in, and then at the 90 degree point corresponding to the voltage waveform, you see that the current is 0 at that instant, voltage is maximum at that instant, and the product is 0 at that instant, as you see in the blue colored waveform. And then further on the power waveform goes positive and traces the positive half of the sign, power sign, and so on, as you would see, you can deduce from the voltage and the current waveforms and then point by point multiplication. So, this is the product curve or the power curve, the blue waveform here. One difference with respect to the previous power waveform as in the case of the resistive load is that here you do not see a DC offset. What is the average value here? Let us unclutter the graph by removing the V and the I waveform and just keep the power waveform, and you see that the average value is exactly 0 for a true inductive load. Whereas, in the case of the resistive load, remember that there was an average value. In fact, that is the crucial difference between the two. Now, consider the capacitive load. We saw this waveform previously again we are going to apply the same process as we did for the resistive set and the inductive set. So, we are going to multiply the voltage waveform in black and the current waveform in red. What do you get? you get the power waveform. Here actually the resultant power waveform in the case of the capacitive circuit is 180 degrees phase shifted with respect to the inductive circuit. This is because the current is leading the voltage waveform. So, at the origin, near the origin, you see that the current waveform is positive, voltage waveform is positive. So, the upper half of the power sine wave is traced first, and then the negative half of the sine wave is traced after the 90 degree point corresponding to the voltage source waveform, and thereby you get this corresponding resultant. P is equal to V I. What do you see here also? We see that the average power is 0, like in the case of the inductive circuit. The capacitive circuit also results in an average power equal to 0. Interesting, isn't it? Only the resistive circuit gives a finite average. Keep that in mind, because we will be using it much later. So, let us put them all together and compare. You see that with R you have a power waveform twice the frequency of the input sinusoidal voltage waveform, but it is shifted, DC shifted as you see, and has a finite, and therefore has a finite average power, non-zero average power. In the case of the inductive load and the capacitive load, the average power is absolutely 0, only that the power waveform is having a 180 degree phase shift with respect to each other. Okay. So, this is the comparison of the power waveform for the R, L and C circuits. What happens if we have an R L load? You see, you now have a combination of an R and an L. And what happens to the source voltage waveform and the current, source current I for such an RL load? You see it alongside. Again we have used the black color for indicating the voltage and the red color for indicating the current. We have a phase lag as usual, like in the case of an inductive load. However, the phase lag is variable, that is, when R is 0, you will have a phase lag of 90 degrees, meaning the current will lag the voltage by 90 degrees, and as R increases, the phase lag starts decreasing. Ultimately, when R goes towards infinity, L becomes very small compared to R, and then it will start going to a unity, start going to a 0 phase lag situation, like in the case of a pure resistive load. Let us have a look at the effect of the R, effect of the resistance on the power curve. What happens to the power curve in the RL circuit as R is varying? Now, that would be interesting. Now, let us have this graph again with the time axis as the x axis and the y axis now showing the power, because we are taking only the power curve, and for an inductive load, start with an inductive load R is equal to 0, we saw that the average power was 0. So, now what happens when R increases? What happens when R increases? That is something that we need to look at. Now, let us say R increases slightly from 0. We will see that the power curve shifts up. There is now a small finite average power as seen from the graph. Further, you increase the R, you will see that the average power gradually starts shifting up. On further increasing the R, the average power keeps on shifting up till it reaches L is equal to 0 value, something like your pure resistive load. So, when R starts increasing towards a very large value, you will reach the condition like a pure resistive load, or L is equal to 0 Henry load, that kind of a situation. Okay. So, you see the way the power curve transforms as you increase the load, and this is as you decrease the resistance. Now, this is as you increase the resistance. So, keep this in mind. Now, in the case of the RC load, something similar happens. Have a look at this circuit in the waveform. You have the voltage source and R and a C, and we are interested in the voltage source waveform and the current through it. The black waveform again indicates the voltage and the red waveform indicates the current. Now, in this case, we see that the current leads the voltage by some phase angle, and the phase angle varies according to the amount of R that you are going to put into the circuit. Now, consider the power curve for an RC circuit. You see that the power curve, as we saw before, we have average power is equal to 0 for a capacitance, pure capacitance circuit, R is equal to 0 ohms. Now, what happens if I start increasing R? It no longer becomes pure capacitance, and gradually you will see that an average power starts developing. So, as you start increasing the R, the average power starts increasing gradually till at a point when the R value becomes so high that it swamps out the impedance provided by C, that it emulates a pure resistive kind of a circuit as though there was no C. So, here again you see that when R is decreased, goes towards average power equal to 0, and as R is increased, you see that it starts going more and more towards having a average power. So, some remarks from these graphs. First of all, the average power is maximum only for pure resistive load. RL and RC loads have some portions of the power curve going negative, and therefore, that portion of the area subtract from the positive portion of the area and trying to find the average, and therefore, their average is going to be much lesser than what was for the pure resistive case, and therefore, the average power for RL and RC loads are going to be lesser than for a resistive case. So, we come back to our basic question, what is power factor? So, let us now give a notional definition, and then later on, of course, when we use the mathematical relations, we can have a mathematical definition. The notional definition will in fact help you derive the mathematical relationship. So, power factor is a measure of the degree to which any given load matches a pure resistance. That is our notional definition. Any load should be either purely resistive or equivalently capacitive or equivalently inductive, or a combination of these. That load which results in a power curve or VI waveform such that it matches as close as possible to the pure resistance or as close as possible to the R or an equivalent R is said to have a very high power factor. In fact, if the load appears just resistive, then we say power factor Pf is equal to 1. And if the load appears purely inductive or purely capacitive, then that is most away from the pure resistive case where the Pf is equal to 0. Okay. And for all other cases, that is RL case, where R is finite, L is finite, and the Pf is between 0 and 1, and we call it Pf lagging. And in the case of RC circuits, where R is finite, C is finite, Pf is again between 0 and 1, but leading. So, we say Pf lead, Pf lag. So, Pf lag is for RL circuits, Pf lead is for RC circuits. However, the Pf value can take values only between 0 and 1. 1 when it is purely resistive, when the load resembles exactly a resistor, and 0 when it is purely like inductance or a capacitance, that is purely reactive. In such a case, Pf is 0, and for all other intermediate cases, you will see the power factor taking values between 0 and 1. Now, we have to learn how to measure power factor. Till now, we had a glimpse of what power factor is. In fact, we made a notional definition saying that the power factor is the degree to which any given load matches a resistive load. Now, we shall see how we go about measuring power factor and quantifying power factor. Always remember that whatever be the load, we will always be comparing it with an equivalent resistive load. Coming back to our screen with the typical graphs of the voltage and the current waveforms with respect to time. We have the voltage waveform in black as usual, we have the current waveform in red as usual. Here, notice that the red colored current waveform is lagging the voltage waveform by an angle phi. This is an RL load. If the current waveform were in phase at 0 with respect to the voltage waveform, then it would have been a pure resistive load. And if it had been exactly at this 90-degree point, then it is a pure L load. And if it had been exactly leading by 90 degrees somewhere here, it would have been a pure C load. Now, this zone from 0 to 90 degrees, any current waveform corresponds to an equivalent RL load. So, let us take an arbitrary RL load like this and try to see how the power waveform looks like. And we saw before that the power waveform is got by undergoing a process of multiplication of the voltage waveform and the current waveform point by point. So, this is the power waveform that you would get. Look here, this portion contributes to the negative power. The power is negative in this region, which means that the power is put back to the source. And in this region, the power is positive and it has an average power which is positive, which says that that is the power which goes to the load actually. It is the active power. So, this power, this average power is the active power, and this portion, the negative portion which is put back to the load, is called the reactive power. So, this is only the power waveform along with the average and the reactive component. Now, we have to always, as I told you before, compare it with an equivalent resistive load. So, let us have two graphs, one for the resistive load or R load, the other for the RL load or an RC load, whatever the case may be. Let us have the voltage waveform which is sinusoidal in shape. Of course, it can be any arbitrary shape, but let us take the sinusoidal waveform, and then you have the current waveform of similar amplitudes, same amplitudes. See that in the RL load it is in phase, it is lagging in the case of RL load. You have the power waveform for the R load and the RL load. See, there is a reactive power contribution, some power goes negative, and as a consequence the average in the case of an RL load is going to be lower than the average of the pure R load. This is the reactive power contribution which goes back to the mains. That being negative means that it goes back to the mains. Now, these two powers, that is the instantaneous powers, its finite average along with the RL load's instantaneous power and its average, we have to compare and arrive at a quantitative value of power factor. So, let us clear up the screen, let us move up, unclutter the screen. Now, this average load which corresponds to the resistive load, we will call it as PR, and this average which corresponds to the average of the RL load power, we will call it as P load. Now, the question is, what is the power factor of this RL load, what we have here? We said earlier that the power factor is nothing but a measure of how close the given load is to a pure resistance or pure resistive load. Let us define PF as follows. PF is defined as P load, that is the average load power of the RL or any other given load, to the average power of an equivalent resistive load, P load by PR. This is the definition of PF. You see here that when PF is equal to 1, which means P load is equal to PR, which means this rises up and this average matches this average only when this rises up and becomes equivalent to this, in which case this becomes purely resistive. And when is it 0? As we saw earlier, when it is purely inductive or purely capacitive, there is no average component in this case, and PF will be equal to 0, and P load is 0, PF will be equal to 0. So, once again we see that PF is defined as P load by PR, where P load is the average power of any given load. It may be an RL load, it may be an RC load or any other arbitrary load, and PR is the average power of a resistive load for the same voltage magnitude peak and current magnitude peak. We will understand this much better as we do few examples. And it should be noted here that the powers are calculated by using integrals. Integral of a waveform is basically the area under the curve. So, it is actually immaterial whether the shape of the waveform is a sinusoidal or any other arbitrary wave shape. So, the powers that we get here, the power values that we get here does not depend upon wave shape. So, whatever may be the wave shape, this definition is valid, PF which is equal to P load by PR. So, let us consider some examples. Consider the same RL circuit and let us try to find the power factor of the RL circuit if we are giving a sinusoidal input. So, let us give a sinusoidal input voltage of Vm amplitude, and this will result in a current of amplitude Im and a phase shift phi. Now, this will have a comparative voltage and the current waveform for the R with the same Vm and Im as follows. See, this should have the same Vm, same Im, but only thing is equivalently in the R case the phase shift is not there, it is in phase with V. So, you will see that the powers in the case of the RL load, you will see some negative portion here, and in the case of the resistive load there is no negative portion, and the average is PR here and the average P load is slightly lower than this because of the negative contribution, because the power is nothing but the area under the curve. So, this area will cancel out the area which is there on the positive side, and therefore, effectively P load is going to be lower than PR. So, let us see what is this PR value for a sinusoidal wave. We know that this peak value in the case of the R load is Vm into Im, half of it is Vm Im by 2. Therefore, PR is nothing but Vm Im by 2. And in the case of the RL load, this portion is called the reactive part, this portion is the active power portion. So, it is actually the active power portion that you have to consider for the power factor, because our power factor says how close does the load match the resistive load, or how much of the portion of the input power is an active power. So, P load is definitely going to be less than Vm Im by 2. So, for a sine wave shape of phase angle, let us say phi of current with respect to the voltage, this P load will turn out to be Vm Im by 2 cos phi. How is this obtained? This is nothing but integral of Vm sin omega t into Im sin omega t minus phi divided over by the period t. So, this will result in Vm Im by 2 into cos phi. Now, what is power factor? Power factor as we defined is P load divided by PR. So, that turns out to be P load by PR, which is cos phi. Therefore, for a sinusoidal voltage wave shape, sinusoidal current which is resulting from the load, you will always see that the power factor is nothing but cos phi, or cosine of the phase angle between the current and the voltage. This is a special case only for sinusoidal, but the general definition of the power factor should always be, you should always go back to our original equation, which is P load by PR, where P load and PR are the average values of the power curves for any arbitrary wave shape. Now, consider this circuit. This is a very common circuit. This is a diode bridge. You see the input is a sine wave here, which we are applying, and there are 4 diodes. This is a full bridge diode rectifier. This is followed by a capacitor which stores the energy, and then followed by the load RL. So, this whole circuit is called a capacitor filter circuit. In fact, this is one of the most common front end circuits that you would find in almost all power supplies, whether it be PC power supplies or whether it be any of the DC power supplies, converters, so on and so forth. All the front ends will be of this nature. Now, how do the various waveforms here look like? Just to get an idea for this capacitor filter circuit, there is the output here. Output is nothing but what you see here in dark. Okay. This sine wave, which is the rectified sine wave, is what you would obtain here, as I am showing here at the mouse points, and only during this portion there is conduction, and therefore, the currents of the diodes here would be of this nature, sharp, okay, and there is no currents any of these at any of these points. This circuit I think you will be familiar with. You would have learned it in some other course, some other class, with these kind of waveforms. Let us now find out what will be the power factor as seen by the input here for this entire circuit along with the rectifier, capacitor, filter. What would be the power factor? So, again we come back to our time grid. You have the time axis as the x axis. let us plot the voltage waveform which is having a amplitude Vm. Let us plot the current waveform for this circuit. We saw the current waveform is a kind of a spiky current waveform as we saw back here. Let me go back again. You see this is the spiky current waveform which is flowing here, which will flow through the diodes, which will also flow through the mains here. So therefore, this is the type of the current waveform you can expect at this point. So input current waveform is of this nature, which has an amplitude Im. How do we propose to go about finding the power factor? Again we go back to the basics. It should be P load by PR. So let us have an equivalent current which has an maximum value of current Im only, but suppose if it had been a resistive load, what would happen? You would land up with a waveform which is having the same wave shape as the voltage waveform and in phase. So in this case, this red line indicates the current waveform that you would have got of the same amplitude Im if it had been a pure resistance. So let us compare V and the red colored current waveform for a pure resistance, V and the blue colored current waveform for the capacitive circuit. So this is the rectifier C filter load, and this is the voltage and the current waveform, and this is the pure resistive load waveforms for an R load which has the same Vm and Im. That is important. Okay. Now let us find the power. Power is nothing but multiplication of the voltage curve and the current curve. So multiplying the voltage and the current curve, all these portions will be 0 in the case of the C filter load. So this portion alone, where there is a finite current and the finite voltage, you will have a power curve. And in the case of the R load, we have, as we have seen earlier, a power curve which is of this sinusoidal nature. Now what about the averages? Taking the average of the power curves, we have PR as follows here, which is Vm Im, this is Vm Im by 2, and P load, which will be average of just this green waveform which you see here. Removing all the other cluttering voltage and current waveforms, you will see this is the power curve, instantaneous power curve, its average for the C load. We say the instantaneous power curve and its average for the R load. Let us move up, clear up the space, and then see that PR is nothing but, as we saw earlier, Vm Im by 2. How do you obtain this? This point here at the cursor point is Vm Im, and this will be the average value which is Vm Im by 2. And this P load, the average will of course depend upon the actual load. It will actually depend upon the area under these curves, okay, which we can get by measurement, which I will tell later on. Okay. So finding the power factor is nothing but P load, this average value divided by this average value, which is P load by PR, which is 2 P load by Vm Im. So therefore, for the case of a C filter load, this is the power factor equation, where Vm and Im is the maximum values of the voltage and the current respectively. P load is the average load power that you are applying, and this 2 times P load Vm by divided by Vm by M will be the power factor. Now let us see how we measure the power for an arbitrary current and voltage waveform or an arbitrary power waveform. Now let us say we have this voltage and current waveforms, and you see these waveforms on the oscilloscope. Let us take measurements, that is measure the points, these points on the voltage waveforms Vk at every, let us say, known instance of time all along the voltage curve for the whole period. Similarly, you measure the current waveforms, that is the red points, all along the current curve whatever may be the curve, it may or may not be sinusoidal for the whole period, okay, ik. Then the average is nothing but Vk into Ik, the product, the product which you obtain, instantaneous product which you obtain for the voltage and the current waveforms, sum up all the products and divide by n, that is the number of instantaneous values that you have taken for the whole period, and that would give you the average for one period. Okay. This is how you can take the measurement of the average power, whatever may be the waveform, because these waveforms you can see on the scope and then note down the values. Let us say, for example, a period you can take some 30-35 samples and then divide by 35 after having summed up the products Vi. Again, summing up, we say that Pf, power factor, is defined as P load. P load is the average power of any arbitrary load, the active portion of the power that is given to the load, divided by Pr, which is the power that you would have delivered to the load if the load had been resistive. As power is an average quantity, you need not actually bother about the wave shape. Whatever may be the wave shape, if you are able to measure the average powers, yes, then you have the values of P load and Pr to measure Pf. One thing you should keep in mind here is what would happen if the power factor is low. So, the power factor is low, it means that P load is low, and if P load is low, which means that there is quite a difference between P load and Pr for the same Im Vm. Now, let us say you want to deliver the same active power. Let us say you have 10 watts of load and you want to deliver 10 watts of active power load with the same Vm and Im as the resistive load. Then what would happen here is, if this has to match this, that this has to come to 10 watts, then these values should go still higher to get that same average, which means for the C filter load the maximum Im will be much higher than what would be for a R load, which means that the ratings of your diodes, the ratings of your power sockets, all those things must be rated much higher for the same output active power load delivery. Therefore, low power factor loads are not recommended. In fact, you have to pay more if you are having low power factor loads, and if you are having unity power factor loads, which means close to resistive load, then you are optimally utilizing the mains or the grid, and therefore you will be less penalized. Therefore, there is lot of scope for having front ends which make any given load look like a unity power factor. Therefore, unity power factor front ends are very important piece of equipments, especially in today's conditions where every equipment has to be certified for having power factors which are more than 0.98 or so. Till now, we have been looking at the power factor without making any assumptions on the wave shape. Even though we have been looking at the slides which are where the wave shapes are sinusoidal in nature, there is no basic assumptions made that the waveforms need to be sinusoidal. And therefore, the power factor, as we stated, that it is the power that is delivered to the load divided by the power that is delivered to the load if the load had been a pure resistance. Okay. Now, you can find out the power delivered to the load as described just previously for the case of the capacitor filter type of load, by measuring the various points of on the wave shape in an oscilloscope, the voltage and the corresponding current, along the time axis for the whole period. Let us say you take something like 30 pairs of points for one period, you multiply and then you average it by the number of multiply V and I, corresponding V and I, add them up and divide by n, the number of sample points will give you the average power. And for the same peak value of current and I, that is the same effective value of I and voltage, if I had a resistance, then it would have been Vm Im by 2 or Vrms Irms. So, that is the absolute maximum that you can get. So, this average which you found out with obtaining the various sample points on the oscilloscope and then dividing it by the maximum value that can be provided with a resistive load, you get the power factor. Now, for a sine wave, you can cross check and see that the power factor is P load, that is given to the load, by Vm Im to 2, or this is P load by V effective I effective. These are effective or root mean square RMS values, as we have discussed in the phasor diagram modeling of the last class or last session. V into I would give you the power delivered to a resistive load, and in the case of the sine wave, V into I is the apparent power which is delivered to the taken from the source and delivered to the load. So, if we talk of the apparent power Vi, so Vi is like that. This is Vi, this is in Va. Now, the power delivered to the load, P load, this is watts. So, watts is given like this, watts or P load in terms of the phasor diagram, and the vectorial difference P load with respect to the Va apparent power and the P load, this would be the VAR or the reactive power, and this angle theta is the power factor angle. So, if you say V I cos of theta will give you P load, or P load by Vi is cos of theta, which is the power factor that we have been talking of in sinusoidal wave shapes all along. And look at the comparison of these two equations, one and the same, the general equation and the specific case what we get for the case of the sinusoidal condition is the same. So, in the case of the sinusoidal condition, P load by Vi, the apparent power, which is basically the product of the effective values of the voltage and current, is equal to cos theta, which is equal to Pf, the power factor. Pf is equal to P load by Vm Im by 2. This is the general equation. Pf is equal to P load by V I, that is V m by root 2 I m by root 2 for the case of sinusoidal. This is equal to cos theta is the specific equation for sinusoids. So, the power factor for sinusoidal waveforms is cos theta. So, we stop at this point after our discussion of the power factor and continue in the next class.